All right, today we're going to take a journey to one of the most extreme places in the entire universe. We're talking about a place where a single sugar cube's worth of stuff weighs as much as a mountain. We are going deep inside a neutron star, right to the very edge of what physics can even explain, to see what happens when the universe gets really, really weird.
So let's start with a simple question. If you take black holes off the table for a second, because, they're technically singularities, what is the single densest object that we can actually observe? Well, the answer is the leftover core of a giant dead star. And its properties are, well, they're almost unbelievable.
I mean, just get this. If you could somehow scoop up a tiny piece of a neutron star, just the size of a sugar cube, it would weigh around 1 billion tons. That's not a typo. 1 billion tons. That's basically the weight of Mount Everest crushed into something you could hold in the palm of your hand. We are deep in the realm of extreme physics here.
So how in the world do you even make something that dense? Well, you start with a truly massive star, way, way bigger than our own sun. When it finally runs out of fuel, its core collapses, and then the whole thing just explodes in this spectacular supernova. Now that explosion blasts all the outer layers into space, but the core implodes, crushing more than a sun's worth of mass into a ball about the size of a city.
Just try to wrap your head around these numbers for a second. We're talking about taking something with maybe twice the mass of our sun, which is almost 1.5 million kilometers across, and crushing it down into a sphere that's only about 20 kilometers wide. The gravitational force it's just almost unimaginable.
Okay, so let's start our journey from the outside and work our way in. We're going to peel back the layers of this thing, starting with what you could call its surface, the crust of the neutron star.
Now, the outer crust isn't a gas or a liquid like you might imagine. Nope, it's an incredibly rigid solid. The gravity here is about 100 billion times stronger than Earth's, and that immense force locks the nuclei of iron and nickel into this perfect, super-dense crystal lattice, all swimming in a sea of electrons. But as we start to go deeper, that insane pressure really starts to change things on a fundamental level.
As we sink deeper into what's called the inner crust, the pressure just becomes unbearable. Electrons are literally getting squeezed into protons, which turns them into more and more neutrons. The atomic nuclei get so bloated with all these new neutrons that they can't even hold on to them anymore. They start to leak out. This process is called neutron drip, and it creates a sea of neutrons that flows with absolutely zero friction. It's a true superfluid. And this is where things get truly bizarre. As those nuclei dissolve under the pressure, they don't just form some uniform soup. Oh no, the forces at play twist and contort the nuclear matter into these strange, complex shapes, creating a phase of matter that physicists have affectionately named nuclear pasta. This just perfectly illustrates how alien this environment is. This stuff, this pasta, is thought to be the strongest material in the entire universe.
So what's on this cosmic menu? Well, depending on the depth and the pressure, the nuclear matter gets forced into different shapes. First, you get these long, rod-like structures that they call spaghetti. Go a little deeper, and the pressure squashes them into flat sheets, which, you guessed it, they call lasagna. And finally, right before the crust dissolves completely, you get these little clumps that physicists call gnocchi. It's a pretty fun name for what is probably the densest, strongest material we can even imagine.
Okay, so we're leaving the crust behind now, and we're plunging into the heart of the neutron star, the core. This is where our current understanding of physics really gets pushed to its absolute limits, and it's where the biggest mysteries are hiding.
So what are we pretty sure about? Well, we think the core is this amazing quantum soup. The neutrons form that superfluid we talked about, flowing with zero viscosity. And at the same time, the protons pair up to form a superconductor, which means they can conduct electricity with perfect, flawless efficiency. And somehow these two bizarre states of matter just coexist.
But that's pretty much where the certainty ends, because as we get closer to the very, very center, the pressure becomes so ridiculously high that, honestly, we just don't know what happens to matter anymore. Do the neutrons themselves just break?
This brings us to a huge problem in physics, something called the hyperon puzzle. See, our best theories predict that at these insane densities, the neutron should actually break down into even more exotic particles called hyperons. The problem is, if that happened, it would make the core softer, easier to crush. That would mean there's a hard limit to how massive a neutron star can get before it collapses into a black hole. And yet, we've found neutron stars that are heavier than that limit. So our observations are telling us that our theory is missing something really, really big.
This puzzle has really opened the floodgates to some truly wild ideas. I mean, maybe it's not hyperons at the center, but another exotic state of matter called a kaon condensate. Or, and this is the most out there idea, maybe the pressure is so immense that the neutrons and protons themselves are obliterated, dissolving into a free-flowing soup of their fundamental building blocks, quarks. If that's true, it would create something called a quark star, a truly alien object.
So why do we care so much about what's going on inside some dead star billions of miles away? Well, because these objects aren't just astronomical curiosities. They are, quite literally, the most extreme laboratories available to science.
You know, this quote really says it all. We simply cannot build a machine on Earth that can even come close to replicating the densities and pressures inside a neutron star. It's impossible. So by studying them, we're actually testing the fundamental laws of nature in a way that is completely inaccessible to us otherwise.
And this has huge implications for everything. Understanding these interiors helps us test our deepest theories of nuclear physics, it helps us explain strange things we see like pulsar glitches, and now with gravitational waves from colliding neutron stars, we can finally get direct data from the source. That data is helping us figure out which of those wild theories about the core is actually right.
So the journey inside a neutron star takes us from a solid crystal crust through a bizarre phase of nuclear pasta and right into a mysterious core where our own knowledge of physics starts to fall apart. The ultimate question really is, what secrets are they still hiding? What new laws of nature are just waiting for us to discover inside these incredible cosmic relics?